this number here is equal to, by theorem 51, is equal to the degree of K over Q. Because K is the splitting field over Q. You're in the characteristic zero situation, so you don't have to worry about the separability hypothesis. That's all right, that's guaranteed. So this degree, the number of elements of Galois group, well, it divides 6 and it's equal to this degree, and then we're now, well, this degree here, it's 3 times that degree. In particular, it's a multiple of 3. So now you see that, okay, so this number of elements of the Galois group, the order of the Galois group, it's a multiple of 3, it's a divisor of 6, it's either 3 or 6. So the number of elements of the Galois group of K over Q is 3 or 6. By the way, now already you can see what the possibilities are for the actual Galois group. If it has 6 elements, then it's the full symmetric group on the set of roots of F. If it has only 3 elements, okay, think about S3. How many subgroups of order 3 does it have? Subgroups of order 3 in S3. So, you know, I'd like to think about this later, but you can easily see that it only has one subgroup of order 3. It's the subgroup generated by any 3 cycle, any cycle of length 3. So you see that there are so if the number of elements of the Galois group is 6, then well, the Galois group is all of then the Galois group K over Q is just equal to the symmetric group on the set of roots of F. And if the number of elements of the Galois group is equal to 3, then this Galois group is K over Q. Well, again, S3, symmetric group on 3 elements, has only one subgroup of order 3. If I call the roots alpha, beta, gamma, the other roots, so roots of F, let's say we call them alpha, beta, gamma, the only subgroup of order 3 on the symmetric group on that set is the following. Then this is equal to subgroup over 3 of the symmetric group on that set is the subgroup generated by 3 cycle. It consists of identity, the 3 cycle alpha, beta, gamma, and the 3 cycle alpha, gamma, beta, which is the square of that. By the way, up to this point, I still haven't used the fact that F only has one real root. This analysis up to this point was general. What we saw is that if you take an irreducible polynomial of degree 3 over Q, now let K be the splitting field, there's 2 possibilities for the Galois group of K over Q. Right? So now, the order of that Galois group is either 3 or 6, and if the order of the Galois group is 3, that means that the Galois group is a subgroup of order 3 of the symmetric group on the set of roots. If the roots are alpha, beta, gamma, well, it has to be that would be your Galois group. On the other hand, if the Galois group has 6 elements, then the Galois group will be the full symmetric group on the set of roots of F. So this was general, but now, alpha, now I want to use the fact that, you know, F only has one real root and see what we can get from that. See, now I'm going to use the result that we did earlier about having the tower of extensions, LKF, and an automorphism of L over F restricting to an automorphism of K. That always happens as long as K is a splitting field over F. Now, you have the following picture. So sigma, take the following. So C, here K, here Q, sigma, complex conjugation. So let sigma be complex conjugation. Q be complex conjugation. Then, okay, so what is, because K is a splitting field over Q, now I'm using that result, the result that we proved. Any automorphism of C over Q, because K is a splitting field over Q, restricts to an automorphism of K. K is a splitting field. So sigma restricts to an automorphism of K. To an automorphism, which is denoted by sigma sub K of K, fixing Q. But now, okay, what's the order of sigma K? The order of sigma K, well, sigma K is just complex conjugation, right? Since F, okay, so how does sigma K act on the roots of F? Okay, now this is the part that we're going to use the fact that F only has one real root. Sigma K is complex conjugation. The roots were alpha, beta, gamma. Alpha was real, the only real one. Beta and gamma, we assume they are not real. They're complex conjugates of each other. As the two-cycle, beta, gamma. Right? So here, this is because beta and gamma are not real. Hence not fixed by sigma K. Let me just write here because these are not real. I think it should be clear. Right. Alpha is real, so alpha is fixed, and then beta and gamma, they're not real. They can't be fixed. They have to be swapped. Okay, so now it acts like that two-cycle. So what is its order? So the order of sigma K is 2, and so your Galois group has an element of order 2. So the Galois group of K over Q has an element of order 2. So 2 divides the number of elements of the Galois group. And then, well, this guy was either 3 or 6, right? So it has to be 6. Is 6, and the Galois group is the full symmetric group on the set of roots of F. So take any permutation of the roots of alpha, beta, gamma that you like. In this case, there's going to be some automorphism of K, which acts like on alpha, beta, gamma in your prescribed way. So to summarize, what we proved here was that if you have an irreducible polynomial of degree 3 over Q, polynomial of degree 3 irreducible over Q, well, so there are two cases. Either it only has one real root or three real roots. What we showed was that if it has only one real root, the Galois group is forced to be the full symmetric group on the set of roots of your polynomial. Okay, we didn't say anything about what happened. So we left it open. What happens if the polynomial has three roots? That's still not answered, right? So in principle, still, so if it has three roots, actually, in principle, we don't still know. It could be either the full symmetric group or just the alternating group on three elements, A3. And in fact, we'll see that both cases are actually possible. If all three roots are real, the Galois group can have, so the different, it depends. It can have 3 elements or 6 elements. Often it has 6 elements, but there are situations where the Galois group only has 3 elements. Okay, thank you very much. I'm going to stop here.